back to my video and to my channel. So now we are going to start a new chapter, that is a electrochemistry of class 12. So in this video we will discuss about the topic electrochemistry, and today the main topic we will consider, that is the conductivity of electrolyte. So let's start the chapter. So what is electrochemistry? First of all, what do you mean by electrochemistry? How can you define the electrochemistry? So we know that whenever the spontaneous chemical reaction, these are converted to electrical energy, or its vice versa, means the electrical energy is used to produce non-spontaneous chemical reaction. Already in class 11 you have studied about spontaneous and non-spontaneous chemical reaction. CR means chemical reaction. So what is spontaneous chemical reaction? The chemical reaction which will take place by their own, those are called as the spontaneous chemical reaction. And what is non-spontaneous? Which can be done by some form of energy, means it needs some form of energy to do the reaction. Those are known as non-spontaneous reactions. So whenever the spontaneous chemical reaction are converted to electrical energy, or its vice versa, the electrical energy is converted to non-spontaneous chemical reaction, is known as what? Electrochemistry. So this is our topic, and this is the definition of electrochemistry. So what is the definition of electrochemistry? The transformation of a non-spontaneous chemical reaction into electrical energy, or the electrical energy is initiating a non-spontaneous reaction, or which produce a non-spontaneous chemical reaction, is known as electrochemistry. So what are the application of this electrochemistry which we will discuss in this chapter? Number one is the electrochemical cell, and second is the electrolytic cell. So these two are the important things that we will discuss in this chapter, that is electrochemical cell and electrolytic cell. And we know that this electrochemistry having many application, and there are some reactions. If I will show you, suppose there is zinc plus copper sulfate. If this solution is there, suppose this is in +2 state, 2 plus, then it will form Zn2 plus, and copper 2 plus will convert it to copper. In this case, the electrical energy is produced. So this is one of the example of the electrochemistry in which the spontaneous chemical reaction is producing the electrical energy. Similarly, there are many non-spontaneous reactions. For example, water, H2O. When electricity is passed through it, what happened? It dissociates into H2 plus O2. So in this chapter it is very interesting. You will know about some reaction in which the reaction will produce the electrical energy, and some reactions are there in which the chemical reaction is driven by the electrical energy, So first of all, in this video our main topic is the conductivity of electrolytes. Number one part is the conductivity of electrolytes. So before going to the conductivity of electrolytes, I want to discuss some important thing related to conductivity. The substance can be classified into three types. Some substances are conducting electric current or electricity, they are conductors. Some are partially conducting, those are semiconductors, and some are do not at all conduct electricity, those are called as insulator. Okay, so in this part we will take some of the conductors which can conduct the electricity. Okay, so which do not conduct electricity, those are called as insulator. Which partially conduct, those are called as semiconductors. And which do not conduct at all, those which completely conduct the electricity, those are called as conductors. So conductors are mainly of two type of conduction we can see. One is the electronic, and second is the electrolytic. Two type of conducting materials you can see, electronic conductors and electrolytic conductors. Okay, electronic means the metals, generally the metals in which the conduction takes place due to the free electron. The conduction takes place due to the free electrons. Whereas in case of electrolytic, it is generally the electrolytic or the aqueous solution of salts, acid and bases, where the current is conducted by the free ions. Currents are conducted by the free ions. Clear? So there are two type of conduction we can see, that is the electronic, in which metals are comes under, in which there are free electrons that conduct the electricity, and there are electrolytic, in which the aqueous solution of salts and acid and bases are there, and there the ions are conducting the electricity. So in chemistry, generally we will take the electrolytic conductors. Generally we are discussing about the electrolytic conductors, because in the previous chapter you have studied about the solution. In solution, I have told you there are some compounds are there which dissociate in the aqueous solution and dissociate into ions. So those ions are conducting the electricity. And electronic, you will study in physics about the electronic conductors, metals, how the metals are conducting the current. Okay, so let's start from the conductivity of cell. Our main topic is conductivity of electrolytes. Okay, so before going to the conductivity of electrolytes, there are some important terms are there which are very important in the point of conductivity of electrolytes. So what are the important points? First is the resistance. Which is generally denoted by capital R. So what is resistance? We know that what in junior classes also we have studied. What is resistance? The opposing force to the current. Is known as resistance. So now we will go in details what is resistance actually and in which factors it will depend. Resistance is directly proportional to length. Length of the conductor. Resistance is directly proportional to length of the conductor, and resistance is inversely proportional to area of cross section of the conductor. Resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. So here we are using, so if we will combinedly write this two, what we can write? This resistance is directly proportional to length and inversely proportional to area of cross section. Okay, now we have to remove this proportionality sign. And there what we will write? Resistance equals to this symbol we are using, and this is the proportionality constant called as rho. Means this symbol is called as rho. And what the rho determines? Rho determines the resistivity. So this rho is called as the resistivity. The symbol of this rho is for resistivity. So what is rho here? Rho is the proportionality constant after removing this proportional sign. Now you see, if we will take the length of the conductor equals to 1 centimeter. And the area of cross section we are taking 1 centimeter square. If we will take the length equals to 1 centimeter and area of cross section equals to 1 centimeter square. So if we will put this here, what we will get? That resistance is equals to resistivity. That's why this rho is also called as specific resistance. Clear? This rho is also called as specific resistance. Why this is called as specific resistance? Because this at unit length and unit area of cross section, the resistivity is equals to resistance. That's why this is called as specific resistance. Clear? Now we will see what is the unit of resistance, what is the unit of resistivity. So let's discuss first resistance. What is the unit of resistance? Unit of resistance is ohm, which is denoted as like this. It is denoted like this. Okay, so the unit of resistance is ohm, which will be denoted by this symbol. Clear? Now if we will take this equation, this is the equation of resistance. So resistance is equals to what? Rho into L by A. Clear? So if we will take rho, then what it will be the formula? Resistance into area of cross section by L. This will be the new formula. For resistivity, the formula will be resistance into area of cross section by length of the conductor. So if we will put the unit, resistance unit is ohm, area of cross section is centimeter square, and the length is centimeter. So what we will get? Centimeter and one of the centimeter will be cancelled out. So finally the unit of rho, that is the resistivity, is equals to ohm centimeter or ohm meter. So this is about the resistance and resistivity. So what is resistance? Resistance is the opposing force to the current. So it is directly proportional to the length of the conductor and inversely proportional to area of cross section. Okay, and here the proportionality is removed by the rho. Rho is called as resistivity, and since at unit length and unit area of cross section resistance equals to rho, that's why this is called as specific resistance. Similarly, the unit of R is ohm. So we can write the formula like this, that ohm equals to resistance into area of cross section by L, and from there we get the unit of resistivity equals to ohm centimeter or ohm meter. So this is all about what? This is all about resistance and resistivity. Next we will talk about conductance. Just like resistance, the opposite of resistance is conductance. So number 3, this is number 1. Number 2, conductance. Okay, conductance. So what is conductance? How can we define conductance? Conductance is generally denoted by capital G. And it is the reciprocal of resistance. Okay, means if resistance is high, conductance is low. If resistance is low, conductance is high. Therefore we can say it is the reciprocal of resistance. Clear? So we can say that G is reciprocal of resistance. So what will be the unit of R? We know that unit of R is ohm. So what is the unit of conductance? Unit of G is equals to ohm inverse, or this ohm inverse is told as, or it is known as Simon. So it is denoted by capital S, and this is the unit of conductance. So remember, conductance is the reciprocal of resistance, means G is equals to 1 by R. So that's why the unit of G is ohm inverse, which is also called as the Simon, which is denoted by capital S. Clear? So this is about the conductance. So related to conductance, third is the conductivity, which is denoted by Kappa. This symbol is for Kappa. Okay, so this is conductivity, Kappa. So remember, conductivity is the reciprocal of resistivity. resistivity. Clear? So conductivity is reciprocal of resistivity. So how can we write it mathematically? How can we write mathematically the formula of kappa? Kappa can be written as kappa equals to 1 by rho. 1 by rho. But what is rho? What do you mean by rho here? So rho is equals to what? Resistance into area of cross section by L. So if we will put the rho value, then kappa equals to 1 by resistance into area of cross section by length of the conductor. So it can be written as kappa equals to 1 by R into L by A. Since 1 by A by L can be written as L by A. So kappa equals to 1 by R into L by A. Remember, what is 1 by R? Here I have told you what is 1 by R. 1 by R is equals to conductance. So kappa can be written as G, capital G. Okay, that is the conductance. 1 by R is the conductance. That's why we are writing it as a capital G. Now what is L by A? What do you mean by L by A? L by A is known as cell constant. Clear? L by A is known as cell constant. So this is denoted by G star. Cell constant is denoted by G star. That's why kappa equals to G into G star. Clear? So in this way we can say that kappa is the product of conductance and the cell constant. So where that kappa is equals to conductance, specific conductance, because kappa is also, this conductivity is also known as specific conductance. Why it is called as? Because if length is 1 centimeter and area of cross section equals to 1 centimeter square. Okay, so here G star will be 1. So here when L equals to 1 and centimeter and this area of cross section is equals to 1 centimeter square, at that time kappa is equals to cell constant, and that's why kappa is also called as the specific conductance. Because at unit length and unit area of cross section, kappa will be equals to the conductance. That's why this is called as specific conductance. Now what will be the unit of kappa? So kappa the unit, you can see it is the kappa. If we will take kappa, here I have told you kappa is reciprocal of what? Reciprocal of resistivity. So kappa is equals to what? 1 by rho. And what is 1 by rho? We can write it like this. Rho can be write like this, that is 1 by R into L by A. So what we will get? 1 by R. 1 by R means what? Ohm inverse. And length is centimeter. Area of cross section is centimeter square. This is centimeter and this is centimeter square. So what happened? This one of the centimeter will be cancelled out. So 1 by centimeter means centimeter inverse. Sorry. So what we can write? Kappa equals to what? Kappa equals to ohm inverse centimeter inverse. Clear? Ohm inverse centimeter inverse. So ohm inverse can also be written as Simon. So the unit of kappa is equals to Simon centimeter inverse or Simon meter inverse. So this is the unit of kappa. That is Simon centimeter inverse or Simon meter inverse, or we can say ohm inverse centimeter inverse. So this is all about the conductivity and conductance. Okay, now you can see how we can measure, how we can determine what the concentration of the solution. How we can determine? We can determine the concentration of solution in terms of what? In terms of moles or in terms of gram equivalent. Why? Because we know that in the previous chapter, in solution chapter, already I have told you that the concentration of the solution can be measured in terms of molarity, that is the number of moles, or in terms of normality. In normality we are using the gram equivalent. Clear? So the concentration of the solution can be measured in terms of moles and gram equivalent. So this conductance or conductivity can also be measured in terms of moles or gram equivalent. Means that unit mole of, or the number of moles of ions or gram equivalent of amount of that ions will conduct how much electricity. So this conductance or conductivity can be measured in terms of moles or gram equivalent. So here one term will come, that is the molar conductivity. Clear? So here a term is coming, that is the molar conductivity. So how can we define the molar conductivity? How you can explain what is molar conductivity? So molar conductivity can be determined how? How we can conduct the molar conductivity? Molar conductivity, first of all I am telling you the definition of molar conductivity, that the conductance in a given volume of electrolyte containing 1 mole of electrolyte. Clear? The conductance of a solution, electrolytic solution, in a given volume of electrolyte containing 1 mole of electrolyte, that is called as the molar conductivity. Which is generally denoted by lambda m. Okay, that is called as the lambda m. So now we will see that this lambda m depends upon what? Lambda m is related to kappa. How? When the conductivity is more, molar conductivity will be more. So that's why lambda m is directly proportional to kappa. What other factors are there, or what other parameters are there on which the lambda m depends? So first is the volume. Okay, first is the volume. So when we will, suppose there is 1 liter of water, same amount, suppose 1 mole of electrolyte is there. When we are taking 1 liter of water, there is 1 mole of electrolyte. But now I have increased the amount from 1 liter to 2 liter. Okay, in that case what we will do? You are clear? When we are increasing the volume from 1 liter to 2 liter, what happened? The ions are getting the free space. 1 liter, suppose this is the 1 liter. So this is the ion, suppose this is the ions. Now it has become 2 liter. The same number of ions, these 4 ions are now getting the free space. So in which the conductivity will be more? In this case the conductivity will be more compared to this one. So when we are diluting the solution, when we are doing the dilution, okay, when we are doing the dilution, in that case what happened? The volume is increasing. So when the volume is increasing, the conductivity increasing. So that's why we can say that the molar conductivity or the molar conductance is directly proportional to lambda m. is directly proportional to lambda m. If we are increasing the volume by dilution, then the molar conductivity is increasing. Next is the lambda m. If we are writing kappa and we are writing the m molarity. Okay, we are writing the capital M molarity. What is molarity? Molarity is equals to what? Number of moles by volume of the solution. Clear? So molarity is equals to number of moles by volume of the solution. So what happened? If the volume is remain fixed, we are taking 1 liter and we are increasing the number of moles. Suppose the molarity is capital M. So what is the number of moles when 1 liter of solution is there? It means M moles. Clear? What happened when the volume is remains same, that is 1 liter, and we are making it M moles, means the molarity is M, means M moles of ions is there, it means the molarity is M. Now we have increased N moles, N or suppose P moles, then the molarity will be P. Then the molar, because the volume is 1. That's why what happened, the concentration, when the number of moles are increasing, the concentration is increasing. When we are increasing the number of moles, what happened? The concentration is increasing. So when the concentration is increasing for a fixed volume, the volume is fixed 1 liter, or suppose it is 2 liter, then it is 2 liter. But we are increasing the number of moles. What happened? The concentration of the solution is increasing. But we know that when in a fixed volume, if the volume is fixed, suppose this is the initial volume, at that time there are two ions are there. Now the volume is fixed and we have increased the number of moles. What happened? According to this one, what you can see, that the number of moles has increased, means the concentration of the solution has increased. But what happened? Now the ions are more close to each other, means there are less free space to move here and there. There are less free space to move around. So when there are less space to move around, what will happen? In that case, the molar conductivity will decrease. That's why I have written here what? That lambda m is inversely proportional to the concentration of the solution or the molarity of the solution. Clear? So why I have written here concentration? Because the concentration is when they are increasing, at that time the molar conductivity is decreasing. Because if the volume remains same, if the volume remains 1 liter, then if we are increasing the number of moles, the concentration of the solution is increasing. So when the concentration of the solution is increasing, at that time what happens? The free space is less. When the free space is less, the molar conductivity will decreases, means when the concentration is increasing, the molar conductivity is decreasing. So lambda m can be written as what? Kappa by m. Why I am writing here m? Because if the molarity is m, number of moles is m by 1 liter, then only the molarity will be 1. If the number of moles is m, here, then it is what? Then it is equals to molarity for 1 liter of solution. So 1 liter, remember 1 liter is equals to 1000 centimeter cube. So number of moles, because the volume is 1 liter, so molarity is equals to number of moles. That's why I have written here m. So 1 liter, it is in denominator, so it will goes to numerator. But 1 liter is equals to what? 1000 centimeter cube. So that's why we are writing 1000. So lambda m is equals to this for this unit, when 1 liter is equals to 1000 centimeter cube, when 1 liter is equals to 1000 centimeter cube. Now one thing is there, if we are writing in terms of meter, what will be the answer? If there is the, remember 1 centimeter cube is equals to 1 centimeter cube is equals to 10 to the power minus 6. 1 centimeter is equals to 10 to the power minus 6 meter cube. So if we are multiplying lambda m equals to kappa into 1000, is into molarity into what? 10 to the power minus 6. 10 to the power minus 6. So 1000, 10 to the power 3 into 10 to the power minus 6. 10 to the power minus 3. So lambda m can be written as kappa by 1000 into m. So this is in terms of meter cube. This is in terms of meter cube. This is in terms of centimeter cube. Okay, this is in terms of meter cube, and this is the formula in terms of what? Centimeter cube. This is meter cube, this is centimeter cube. Clear? Now if we will see the units, okay, for this one, if lambda m equals to what? Kappa. What is the unit of kappa? Kappa unit is Simon centimeter inverse into, here 1000 centimeter cube is there, so centimeter cube. What is the number of moles? Mole. M is the number of moles, so here mole. So lambda m is equals to what? Centimeter, Simon centimeter square mole inverse. Simon centimeter square mole inverse. And this unit is very, very important, because during the numerical you have to convert from one unit to another. Similarly, if we will go in terms of meter, then lambda m is equals to what? Simon meter square mole inverse. Simon meter square mole inverse. So these two are important units of molar conductivity. Okay. So similarly, there is equivalent conductivity or equivalent conductance. Equivalent conductance. So what is equivalent conductance? Equivalent conductance, lambda eq. Okay, so here kappa into 1000 by n. Kappa into 1000 by n. And this is also we can write kappa by 1000 into n. This is for centimeter cube. This is for centimeter cube, and this is for meter cube. This is for meter cube. Clear? So now the thing is that when we are getting their so what will be the unit from this one? So here the equivalent conductance unit will be Simon centimeter square gram equivalent inverse. Here the mole inverse is there. Here we are writing gram equivalent inverse, because in normality we are using the gram equivalent. Similarly, it is Simon meter square gram equivalent inverse. So these are the important formulas and the important units of molar conductivity and the molar conductance and the equivalent conductance. This is equivalent conductance and this is molar conductance. Clear? So in this way we have talked about the conductivity and the molar conductivity. And remember, one more thing is there. When we are writing alpha is the degree of dissociation. So degree of dissociation is equals to lambda m by lambda m naught. So here this is the molar conductivity or conductance, and this is called as limiting molar conductance, which we will discuss later on. Limiting molar conductance. Clear? Okay. So this is about the alpha. Now last we will see the factors affecting the conductance or conductivity, factors affecting the conductance, factors affecting the conductance. So number one is the nature. Number one is the nature. For example, if we will take in terms of electronic conductance, means in metal, in the case of metals, silver is more conducting than gold. Silver is more conducting than gold. Similarly, aqueous NaCl is more conducting than pure water. We know that pure water is a poor conductor of electricity. So aqueous NaCl is more conducting than the pure water. So these two, electronic as well as the electrolytic, both will depends upon the nature. Both will depends upon the nature of the substance. Number two is the temperature. Temperature. Remember, in temperature, when we will take the electronic conductance, it increases with the decrease of temperature. Increases with the decrease of temperature. Decrease of temperature. Clear? It increases with the decrease of temperature. But when we will talk about the electrolytic conductance, in case of electrolytic, what happened? Electrolytic, it increases with the increase of temperature. It increases with the increase of temperature. Clear? It increases with the increase of temperature. This is the electrolytic conductance. Clear? Next is this molar conductivity. Molar conductivity is directly proportional to dilution. This is the third factor. Means upon dilution the molar conductivity increases. Upon dilution the molar conductivity increases. And fourth thing, it is inversely proportional to what? Increase of concentration. Inversely proportional to concentration of electrolyte. So these are the few factors on which the conductivity and the conductance depend, in which it increases or decreases according to these factors. So in this video we have discussed about the conductivity of electrolyte. So in the next video we will discuss about the conductivity of weak and strong electrolyte and the Coulter's law, and then we will discuss some of the numericals related to conductivity of cell. Thank you and have a nice day.